So, how you guys doing? So, main thing is that this is the start of test week. Some of you might take the test in the afternoon, some of you might not. You're allowed to pick a time, as long as it isn't Thursday. And my goal for lecture today and also for this week is primarily to focus on questions you guys have or encountered while working on homework, practice test, also quizzes in addition to the homework, and anything else on your minds leading into test time. So, what's on your minds?
Is there any way that we could go over number one on the practice test or something like it? I think that's the vector edition.
We absolutely can. We can go over anything on the practice test or homework you guys want. So number one, here we have vector addition. Plane is flying northeast or at a certain speed northeast at a certain speed, followed by southeast at a certain speed. Find the wind is blowing southeast while it is flying northeast, and we have to figure out the resulting magnitude and direction of the plane's velocity. The wind blowing on the plane is going to cause it to veer slightly off course, and we need to figure out by how much. Something pilots have to deal with on the reg. So here we've got the two vectors, drawn tip to tail, as I'm fond of doing. And before they can be added, they have to be divided up into their components, because we have to add just the x to the x and just the y to the y. Now, weird thing about 45-degree triangles is that the two legs will be the same number. So the two legs of the 350 meter per second vector will both be 247.5, and the two legs of the 55 meter per second vector will both be 38.9. But it's worth noting what direction all of the above point in, because the x components of the two triangles do point in the same direction. They are both blowing easterly. However, the y components work against one another. You've got a very big north component and a much smaller south component that are being added together. So when I bring those two vectors over here to actually do the vector addition part, I have made the south pointing y component of the smaller of the two vectors negative, so that it actually subtracts from the y piece of the first vector, and as a result the x and y legs of the overall summation are not the same. Any questions leading up to that point? All right. Now, this is technically the component form of the final answer. The final speed of the plane is 286.4 east and 208.6 north, which you could use to figure out, say how far you're going to move in each direction over an hour. But what is being asked here is, what is the final magnitude and direction of the plane's velocity? So we need to know, if we were to draw those two out as the legs of a right triangle, we need to know the angle and the hypotenuse. So these two pieces here are using the Pythagorean theorem to find the hypotenuse, 354.3, and the angle, tangent theta equals the y leg over the x leg, and therefore theta should equal about 36 degrees north of east. How's that feel? If my answer key is hard to read, I can rewrite this on the board in bigger print, if that is an issue for anybody. This file is also uploaded to Brightspace though, so you can just pull up this PDF on your own screens if you want to see it more closely. So I'd call this one a vector addition question. Main things to note are one can only add x to x and y to y. So first the components have to be divided up, and then they have to be reforged into their final summation. What else is on your minds?
Can you go over number 5? I think it's the tension one.
All right. So, yep, flower pot. So, the question here is, what is the tension in each of the two rows? And this is similar to some of the tension addition questions we've done, where we say had a couple of weird pointing ropes all holding something up, and we had to find the tension in each one. Main difference between the one from class and here is only 2 ropes, and their angles are actually kind of mirrors of one another, rather than all of them being different. So we really only have to analyze all the forces acting together on one point, and I recommend we consider all the forces acting directly on the flower pot. So what I've got on the answer key, but also over here on the board, because my other sections asked about this one as well, looking at the net force on the flower pot in both separately the x and y axes. And my first question to you would actually be, what is the net force acting on this hanging flower pot? Before even doing any math, just looking at this picture, looking at the general type of question, looking at the physical premise of the question, what should the net force on this flower pot be? 0. And how do we know that? It's not moving. Specifically, it's not accelerating. So Newton's second law says net force equals mass times acceleration. And if A is 0, net force is 0. So if an object is holding still or moving at constant velocity, either or, this is automatically true. And that means that net force in both separate axes must be 0. And we can use that to our advantage. Again, automatically true if something is being held in place, and that is usually the purpose of tying something up to hang, is that you want it to remain still. Architects, their whole job is make sure every force in the building adds up to 0. Because if part of the building is accelerating, you don't have a building anymore, you have a crash site. So over here, just to kind of, I had this written down from earlier to make it clearer than up there, is the net force in each axis on the flower pot. In the x-axis, the only x forces here would be the 2 x components of the 2 tensions. So T2x pointing left and T2x pointing right and T1x pointing left, sorry. So those are the only 2 x forces present. And again, net force overall is 0, which means separately in each axis, the net force must also be 0. So that just leaves us with T1x plus T2x equals 0. The x components must be canceling out. And in the y-axis, there's actually 3 forces present because the 2 ropes are both pulling up in the y, so here is their y-axis legs. But then separately, if we consider these the forces acting on the flower pot, we also have the weight of the flower pot pulling down. So vertically speaking, the y components of tension are teaming up to negate gravity. And so this is, I would view, our starting point and kind of what would work us towards a 2 equations, 2 unknowns type scenario. questions about the starting point? This is questions about this as a starting point. Okay. Now I'm considering weight to be known because we know the mass of the pot. We can figure out its weight. It would just be 10 kilograms times negative 9.8. So if I consider that to be known, as these equations are written, there's technically still 4 unknowns left because we don't have numbers for either leg of either vector yet. So what I did over here is do as much work as possible to try to divide the unknown tensions up into their XY components. We don't have a number for tension, meaning we can't get numbers for the XY components, but we can at least rewrite them in terms of the tensions that we're after. For example, I labeled this vector T1 because I'm left-handed and working from left to right. So T1 would have an X component of T1X, a Y component of T1Y, sine of 60 degrees, opposite hypotenuse. Sine of 60 degrees would be its Y leg over that unknown hypotenuse. So rearranging that for the unknown T1Y would be T1Y equals the unknown T1 times sine of 60. And we don't know T1, but T1 is what we want, right? Which means by solving for this, we can now write T1 sine 60 over here instead of TIY. And that gets rid of TIY and instead replaces it with just T1. And just T1 is one of the things we want. So the rest of these are just the process of turning the unknown components into a trig function that relates instead to the tension directly rather than to its legs. So same thing to T1, but in the x-axis, cos 60 would be T1x over T1, therefore T1x is T1 times cos 60. And as long as you know the angle, the cos 60 or sine 60 is just a number. You can find a number and write that instead. I kept it sine and cosine, but you can find a number for it if you prefer to work that way. And frankly, since T2 is pointing at the same angle, T2's legs would look pretty similar. Its Y leg would be T2 sine 60 and its X leg is T2 cos 60, since the angles are the same. And with those components written, we can plug them into these equations rather than leaving them in terms of the unknown legs that we don't have numbers for. And that takes us from 4 unknowns down to 2, because now it's all just about T1 and T2 directly. So in the x-axis, instead of T1x, we put T1 times cosine 60. Instead of T2x, we put T2 times cosine 60. The main caveat being, note that the x components work against one another. One points to the left and one points to the right. So one of these has to be put in here with a negative sign. If we don't add that ourselves, it'll bite us later. Any questions getting to this point from here? All right. Now, I just decided to add the negative 1 over to the other side, just so that it's even and the negative signs are all gone. And normally this would be one of our equations with our 2 unknowns in them. So we can also plug the y legs into the y-axis one, and we would have 2 equations with 2 unknowns, T1 and T2. So at this point, we can do our usual 2 equations, 2 unknowns. We can solve this one for, say, T2 and plug it in down here. But there's a curious thing about this particular question, because if we take this equation and try to simplify it, like say we're trying to solve for T2, we divide both sides by cos 60. Well, there's a cos 60 on both sides, so it just kind of cancels out. And in an attempt to solve for T2, we end up at T2 equals T1. The 2 tensions are the same, whatever they are. So this is technically one of our 2 equations, 2 unknowns. This is kind of like the most useful thing you can have in a 2 equations, 2 unknowns, because it means that your 2 unknowns are the same thing. And so there's really two ways you could think of the other equation from that point moving forwards. You could, as we usually do, solve it for one, plug the other in, and then get the answer. But what I did in my own work is I just kind of stopped caring about T1 or T2 when I just wrote T from that point on, since I'd proven that they're the same thing. And ultimately either option, like what I've got here in black, is keeping them separate, solving for one, plugging in the other. But you could also, again, just make them both T's, compress from there. Either way, you should end up at both of them being 56.6. So it is vector addition, specifically vector addition, Newton's second law, net force equals 0. Vector addition, because we're looking at the two separate axes, and two equations, two unknowns. Just kind of a interesting take on that, since they happen to be equal to each other. But we still had to prove that before we could do anything with it. How's this one feel? Better?
Yes, thank you.
Welcome. Now, so if I could ramble for a sec. My students frequently voice to me their dislike of trig, which is valid. And as a result, students have also voiced to me that they are not very fond of this type of question, because there's a lot of trig involved and a lot of axes work to deal with. So in an attempt to be as non-vague and as helpful as possible, there is a question similar to this on the test. But I will say again, I write my test questions knowing that, I write my test questions such that the test should be something that you can comfortably do by yourself in an hour. You have more than an hour, but I write it as if you had an hour. And for that reason, when I write my test questions, I don't try to make them things that should take you a long time to do. I try to make them intuitive, and I try to make them something that you can complete pretty quickly. Because if there's 9 questions, you're meant to average like 1 every 7 minutes. Again, you have 3 hours to take a 1-hour test, but I'm still writing it as if it was 1 hour. And for that reason, I try to make my questions in such a way that write them such that it rewards you for understanding the concepts, but doesn't require you to spend 30 minutes on a single question just staring at it doing lines of algebra. So there is a question similar to this on the test, but I have written it in a way to simplify the process to not take too long. Did my message get across there? Okay. So there will be 2 equations, 2 unknowns type scenarios, but they might simplify out in a way that you wouldn't expect. In a way that's beneficial. Sorry for being vague. What else is on your minds?
For number 9, I just have a quick question. Is work always equal to kinetic energy?
That kind of depends on the scenario. In this question, yes, because the goal of doing work is always to give energy to something. So when the baseball player does work by throwing the ball, they are burning up and giving this energy to something. This energy has to go somewhere, and the point of throwing things is typically to be giving energy to whatever you're throwing. So this energy has to go somewhere, The point of the task was to give energy to the ball, and so that's the only place it can end up. So, depends a little bit on the situation, but the rule I would give is the energy used up by work always has to go somewhere. So, typically the way I word the question, it's to go into whatever's being worked on. Does that answer the question?
Yes.
Okay. How you guys feeling? It's okay if you don't know, because it's the first test of the course. Like, you don't have a frame of reference for it yet. So I'll just try to say as a comfort again. My entire course is weighted in such a way that no one grade will ever destroy your average in here if you just have a bad day. That includes both tests and also the exam. Where is my syllabus? Where did I put that? For example, this is the weighting that I put on the syllabus. Tests as a whole is 38% of your grade, but that means each single test is about 19%. Meaning, if you did hypothetically get a 0 on one of my tests, which is next to impossible, you could still get an 81 in the class. And that's if you got a 0 on the first test. You'd have to get a 100 on everything else, but that's if you still got a 0. And again, the only way to get a 0 for me on anything is to leave it blank. You could write a frowny face as your answer for every question and get a 10%. Because that's an answer, it's just not a good one. Which again raises the margin of error on what your final course average could be. So my main tip is leave nothing blank. Have an answer for everything, even if it's you think a bad one. I've given points for someone drawing a sketch of Yoda before. Specifically, it was origami Yoda pleading for bonus points or partial credit.
Can we turn the entire test into an origami Yoda?
I would rather you not, because I'm gonna have to unfold it to look at your answers anyway. So your work would sadly be destroyed, and I would hate that. Now, once I give you the test back, you can turn it into any sort of art piece you want, but that I still wouldn't recommend it, because part of the reason I let you keep the test is so you could use them to study for the final. So do what you will with that information. So leave nothing on the test blank. And I create my answer keys. When I make my answer key, I also assign points for all the things that I'm looking for. It's not a hard and fast rule, because sometimes students do things I'm not expecting. And so whatever I write as my point calculations is fluid depending on what a student does. But everything you do is worth points. Like, every single step in the math of my answer key, I assign projected point values for. So if this was like a 10-point question, you get 3 points just for writing down this formula, and maybe 1 point for actually using it correctly. And then over here, another 3 points for writing down this formula, so on and so forth. So everything you write is worth points. I'm especially looking for good sketches for, say, the projectile motion question. I give points for just doing this, especially if you show the velocity vector getting divided up. That's something I'm looking for. Especially in this sort of question, I'm really looking for using equation 3, specifically once in each axis. There's a lot of points assigned just for that. There's ways that don't involve formula 3, that's just my expected route. So writing that down big point sink on this one. Like if this was a 20-point question, that could be worth up to 10 points depending on what other elements I'm looking for. Because like, in my perspective, the question kind of hinges on Formula 3. There's some other ways you could do it, but this is what I feel is the most common way. So pictures, writing down formulas, and honestly, just getting formulas down kind of kickstarts the thought process, I find. So if you're like stumped, please go through the process of like writing things out on the sidebar like I do on the board, writing down the formulas you're gonna use. And if you're still stumped at that point, one, please ask the proctor to make sure that you understand the question, because I want to make, like, you're allowed to ask questions. Me or Dr. Edwards can't obviously give you the answer, but we can at least make sure you understand what's going on, what's in the question, what's being asked. So please ask questions. And if after that you're still stumped, if you've got the formulas written down, just stare at them, play with them for a second, plug things in to see what sort of things you end up at. Because again, that's work that leads you to an answer, even if it's not a great one, and that might jumpstart your thought process to the correct option. And even if after all of that, you still don't get a numerical answer that you are confident in, write out a sentence or two explaining to me the concepts that are going on. Because even though I write this like a math question, like I'm looking for a numerical answer, what I'm grading for is seeing that you understand the concepts. Ideally through the lens of math, but not necessarily. You could, like, it's possible to get an A on my test without ever actually arriving at the full final answer for every question, as long as you put the right formulas in and do most of the work. And maybe like you make one algebra mistake at the end and you technically never get a number answer right, you can still get an A. Because I'm looking again for the formulas and using them right. If you make one algebra mistake on each one, you can still get enough points to make an A. And even then, if you start feeling it on the algebra, like say you're looking at this question and you're just drawing a blank about how to use Formula 3 on it, for example, or any other displacement, velocity, acceleration formulas, if you like write out to me that you understand this is a projectile, it's accelerating in the y-axis, but it's still moving in both axes at once, two-dimensional motion. You know, explain to me anything that you do understand about what's going on. That's just more points. Because I'm again looking for your understanding of what's going on, even if you don't demonstrate it purely through math. I like math, but I'm the kind of sicko who majors in physics by choice. You'll also, again, still have your calculator and formula sheet. If you don't have a printed copy yet, I will have spares at the head of the room.
What can't be right on the formula sheet?
Please do not write out like the entire laws of motion. I don't ask you to memorize much, but I do at least want you to be able to recognize them from memory. So don't write out all the laws of motion, and don't write out fully worked out examples. Especially if they are somehow the answers to the test questions, which you shouldn't have in the first place. So I guess that's rule number 3. Don't write down the test question answers, because if you have those, that's a separate issue.
Does that happen before?
No. I only bring it up as a joke.
Okay.
I don't want it to happen. I just anticipate with my luck that somehow it will, and it like shouldn't, but it's a big universe. I'm just rambling at this point. How you guys feel? Anything else on your minds for right now? The lectures this week are going to be very low impact. Again, I want to make sure that everyone's okay for the test, and so I'm not going to introduce any new material until everyone's finished the test. So we're really not going to learn anything new this week unless you like get me on a rant about how Superman's powers work or a similarly nerdy question. Next week, I'm going to give the test back and begin starting chapter 6. But I won't officially begin any new material until then. So once you're done with the test this week, you can kind of take the rest of the week off. If you haven't taken the test, show up, maybe get a free study session in, or you can just skip class if you want. You're adults, you can decide. If there's nothing on your minds, I want to at least make one more point for the day, because across all my lectures, there's some common things students ask about. I want to make sure that you guys have this, like all my sections have the same information. I believe I have told everyone to put this triangle on your formula sheet. This is in reference to a question like practice test number 8, where we've got an object sitting still on an incline and normal force is no longer equal and opposite to gravity. I'm going to begin a monologue real quick about putting that triangle on your formula sheet and why it's going to be like. It's Monday and I already can't talk. It's a good sign. This is something that as a physics major took me a year to fully wrap my head around and be able to do by myself without having this in front of me first, which is more justification for you to please write this down. It is a tool you can use. And again, its purpose is to show the relationship between the forces acting on the object while it is sitting on the ramp. The way that this is specifically drawn with static friction here, this is if the object is sitting still on the ramp, which, cough, cough, very useful for this test, cough, cough. You didn't hear that. And when I was a student, the thing that I had the hardest time wrapping my head around is why the 30 degrees went there, which is something that, students this year have been asking me too. So to try to elaborate on that, the purpose again is to take this free body diagram, which shows the 3 forces acting on this object as it sits still on the ramp. Gravity down, normal force out, perpendicular to the ramp's surface. And since the box would try to slide this way in a frictionless environment, friction would act in the opposite direction to hold it still, so that's why I've got static friction pointing up the ramp. It's always opposite the attempted motion. All 3 of these vectors, if the box is sitting still, should add up to 0. And you could do the normal net force equals all the forces added together here. Trouble is they're all pointing in different directions and there'd be a lot of trig involved in that method. So instead, what I do is, if they all add up to 0, I know that these 2 are at a right angle to each other, because normal force has to be perpendicular to the slope, and friction has to be parallel to the slope, because the slope's surface is what's making it to oppose that parallel motion it doesn't want to happen. These 2 things are perpendicular, so physically, to create this from this, I take all 3 of these vectors and I don't even rotate or resize them, I just drag them into a triangle shape. Normal force, friction, gravity. They're all pointing the same way. They just aren't sized correctly because I'm not an artist. And when you drag them like this, they form a right triangle where, coincidence of coincidences, the angle between normal force and gravity is the same as the incline. And separately, the angle between normal force and friction is always the right angle, because by definition it has to be. Normal force is perpendicular to the slope and friction has to be parallel to the surface creating it. So the right angle always goes there and the ramp angle always goes there. And there is a reason why. The rule is normal force and gravity are always at an angle equal to the incline. And that is always true even on flat ground. What's the angle between gravity and normal force here?
180. Or
You're not wrong. You're not wrong. What would be so let me rephrase that. If I did the same thing over there where I dragged the vectors tip to tail to try to add them, and I physically drag gravity to the tail of normal force, What's the angle between those two lines? It's 0. They overlap, they're totally parallel. Parallel lines, 0-degree angle between them. What's the angle of this slope if it's flat ground? 0, it's flat. So even here the rule holds. There's 0 degrees between gravity and normal force on a 0-degree incline. And I find it useful to like compare extreme cases when I'm trying to drive a concept home. The opposite extreme would be the normal force acting on an object being pressed horizontally into a wall. This is a 90-degree incline. Normal force is now at 90 degrees from gravity. So those are the extreme cases. So now I'm going to switch to slightly less extreme cases. Here we got a shallow angle, normal force, gravity. I'm going to take gravity, drag it over here tip to tail, and that shows that there's a very shallow angle between normal force and gravity. Here's an extreme angle, about 70 degrees here. Drag gravity over, about 70 degrees there. So if I had a model that I could like physically scroll to show the transformation here, that'd be something that'd be worth my time to make actually. I could physically show the incline and physically you could see the angle scaling with it. Again, this took me a year to get my head to fully be able to do by myself without seeing this image as a physics major. So please write this image down. Rant over. Anything else on your minds for the time being? All right. We can call it for today. Feel free to stick around in case questions pop into your head, but it's about lunchtime anyway. So I'm going to tentatively call it here. I had a point where it could go. Remember that you can take it any day of the week except Thursday. So if a day besides your normal one agrees with your schedule and your study habits, go for it. You don't have to email me or Dr. Edwards, just show up. Show up to this room, not the lab room. It's because there's more chairs in here and they're all facing the same direction. And bring calculator, formula sheet, maybe a snack. You've got 3 hours to take a 1 hour test. So, and if you have academic accommodations, please let me or Dr. Edwards know. Time-based accommodations are kind of already handled. It's an hour test and you have 3, so time and a half would still be an hour and a half in 3 hours. But if you need, if you have like separate room accommodations, just remind us and we will make that happen. We have other rooms in the building we can use. And let me know if you have any other questions while studying, and have a great day.